Alright, so in this lecture, I'm gonna be talking about another approach for event extraction, but this time it is generative, and it is a kind of generative model that we are conditioning it, and conditioning based on knowledge base. And the name of this model is called KCGEE. It means knowledge conditioning generative event extraction. So I'm gonna be focusing on this paper from Monash and in 2023. Event extraction is an important but challenging task. Many existing techniques decompose it into event and argument detection or classification subtasks, which are complex structured prediction problems. Generation-based extraction techniques lessen the complexity of the problem formulation and are able to leverage the reasoning capabilities of large pre-trained language models. However, they still suffer from poor zero-shot generalizability and are ineffective in handling long contexts such as documents. We propose a generative event extraction model that addresses these limitations. A key contribution is a novel knowledge-based conditioning technique that injects the schema of candidate event types as the prefix into each layer of encoder-decoder language model. This enables effective zero-shot learning and improves supervised learning. To bridge this gap, we introduce a novel technique called knowledge-based conditioning. This approach involves injecting event type information as prefixes on different layers of the underlying pre-trained language model. By incorporating this information, we aim to improve the performance of event extraction tasks. Additionally, to address the challenge of adapting to new scenarios, we consider event extraction from the perspective of zero-shot learning. So we create prefix by prefix generator. And the rest of that is just sequence to structure model. So there are three contributions. First, they propose a novel knowledge-based conditioning technique that injects event type information, so that's enables zero-shot learning. Then we carefully design a prefix-based injection that incorporates cross-attention because we want to improve document level into event extraction. Then we conducted extensive experiments on two benchmark datasets in both fully supervised and zero-shot settings. Our evaluation consistently shows strong performance across all settings. In particular, our model achieves substantial superiority in the challenging setting of document-level event extraction and zero-shot transfer, outperforming state-of-the-art models up to 5.4 F1 points. So we compare this model with other prompt, because there are many prompt-based generative models. For example, BART generative model, Jigri, and the many other things. As you see, that all of them have encoder-decoder, but for this model in this paper, we are using multiple events. It's not just like a single event here, it's multiple events. But here we are doing conditioning, and not only decoder conditioning, but also encoder conditioning, because we have different candidate event types, and then we can find event detection, trigger identification, event argument extraction as a generative model. So the generated sequence is a linear representation of events mentioned. For example, event 1, this is trigger, this is relation, role and argument, role argument. For it, so for any event, we have event type, trigger, and role and argument. Then the next one. So it's a generative model. It's LLM. It's like a generative language model, but first we generate for the first event, then we generate for the second, from left to right. So we encode it with a multi-layer transformer, and then the decoder is again transformer based. And the conditional probability is just the product of this. This is the classic thing. So this paper investigates the best way to leverage pre-trained language models as the backbone encoder-decoder model for event extraction. Using pre-trained language models is now standard practice in NLP because of their good performance and generalization. So here is the concept of prefix that we want to talk about. It's like input and output, but some of them, these areas are freezed, and the rest of them are variables that should be trained. So the gray blocks indicate the frozen. When you see this gray block, it means it is frozen. And it's a template, something that is frozen. These are the weights, so because they mean the weights, so the weights are frozen. Those parameters are frozen. So this is an illustration of the end-to-end framework where the main architecture is a transformer, encoder, decoder. You see the lower part, for example here, represents conditioning, because we are conditioning not only for encoder but also for decoder. For decoder, we are conditioning like this. So we are conditioning it. We condition the encoder on event types of the underlying event extraction task. So given event types, we use the encoder to get the encoding representation of event types. We then combine these event representations through a function to create event conditioning context. Since we assume each event type is equally probable a priori, we use the pooling average operator, and this vector is used by a prefix generation network that I showed you to produce that prefix. Again, for decoder, we are using conditioning. It is expected that the representation of instances could help downstream generation in the decoder, as we use representation of both the task and the input document to create a prefix for the decoder. Specifically, let h sub x denote representation of the tokens of the input document x. We combine the document representation h sub x and the task, this is the task representation, through these function f of decoder. So f of decoder is based on dot product based cross attention. It's just a cross attention, and the resulting fixed dimensional vector summarizes for decoder condition. But how do we generate that prefix? There is another module, we call it prefix generator. We create the encoder, z sub encoder, and decoder prefix. So we just generate them. And k is the length of injected prefix. And this is the cardinality of h sub I. The number of parameters of the ith injected prefix maintained in the transformer architecture. With the injection of z encoder and Z decoder. The encoder and the decoder are then modified, because now we are conditioning them, not only encoder but also decoder. And for training and inference, we just use negative likelihood. And the data set, they used ACE 25 for evaluation metric. They just use F1 score precision and recall, but for not only for argument extraction, but also for trigger classification. And so they have these two data sets. For training, they use this amount, for development and test. And the instance is one, they tested for one sentence. The data set is, so ACE is one sentence. But that's why they use wiki events, because if you want to validate your model for cross-document, so you need to use another data set, which is wiki events. And the events are multiple events. It's not only single or sometimes multiple. It's always multiple. So it's very hard. But the training data, because it's expensive, the training data is not that big. And it is more complex because the argument, we have 59 argument types, although the event types is the same, but the argument time, there are many argument types. So it's more challenging data set. And you see the difference between F1 score. So state of the art is less than 70%. And this is for trigger classification, but for argument classification, it's just 51%. So they outperform many state-of-the-art models. I've explained this one. I've explained this one. And so these are experiment results for zero-shot learning on sentence level and document level datasets. So in any ACL paper, we should write limitations as well. So we explore a new method for solving zero-shot. The model has the ability to zero-shot transfer learning, primarily from scene role composition. This means that although the model has not seen any instances of zero-shot event types during training, the schema of these event types is available in the training stage. So there is still a gap for true zero-shot generalization.